Yeah, thank you, Claire, for inviting me, and thanks to Honeywell as well for putting this on. I think before I get started, I just want to acknowledge, so Keenan and I met, I think in February 2014, something like that, right when both of us were at the early stages of what we're now doing now. So it was super cool seeing the progress you guys have made. It's incredibly impressive. So I'm excited to talk a little bit about what we're doing at Skydio. And I want to start with a couple of videos on kind of both ends of the spectrum of what's possible in terms of experiences that you can have with a drone. So this first video are clips off of YouTube of people flying today's consumer drones.
Intention of doing a bit of mountain bike riding, enduro riding, bit of surfing, rock climbing, abseiling, and I was hoping that the drone would pretty much control itself and video me while I just left the remote wherever. So this is on follow me mode, and this is my first run attempting to just let the drone
get more and more disappointing as we go along.
Yeah, it ended I actually got lucky, didn't damage it much, but you'll see in a moment that the old collision avoidance, it's great, but can't really pick up small branches. So back to the drawing board.
I would argue that branch wasn't that small. And probably should have seen that. So the second video, this is actually an older video. So this is an RC airplane competition. RC airplanes were kind of the predecessors to drones. And this is the world that I grew up in. So I grew up flying competition RC aerobatics. This isn't me. This is a guy who is one of the best pilots in the world. And he's flying his freestyle sequence here. So it goes on, and it's all pretty cool. But my guess is a lot of what he was doing there is pretty surprising to people, and probably beyond the capabilities of what most people thought flying systems could do. But I think the really key thing here is that with a manually flown system, the capabilities of the drone are basically determined by the skill of the pilot. And this, if you look out in terms of what people are doing in drones today, like this is most of what's out there. Most drones are manually flown in some form. And you know, what you see in that second video is the result of like the 10,000 hours. I mean, he's been practicing that for his entire life. And there are people who have that level of skill or that proficient that can do incredible things. But the average case is not very good. And that really is the motivation for starting Skydio. If you build a fully autonomous drone, and there's spectrum of autonomy we can talk about, but if you have something that's fully autonomous, the capabilities of the drone are determined by software, and that's an incredibly powerful paradigm because it means that you can have the creativity of the best software developers in the world for any particular application, and then that capability can be available to anyone, anytime, on demand. So the motivation for Skydio is we just felt like there was a big gap between the kinds of concepts that were possible, that people were excited about with drones, and the average experience of doing something with one. So this is a snapshot of our current systems. This is the Skydio R1, which we launched earlier this year. So the task here is it's following and filming the person, and this is all fully autonomous. So we'll talk more about how this works, but basically it's using computer vision and AI to do everything in all of these videos. So this isn't a surprising idea. I think that autonomy is is important. The challenge is that it's really hard, and I think that a lot of what we've seen over the last few years is people realizing how hard it is to build a fully autonomous system that does useful, interesting things for people. And Keenan could speak to this as well. I think one of the real success stories of Zipline is that they picked a problem and crafted the whole thing in such a way that you could deliver meaningful value without having to do a lot of this nasty stuff of flying in close to the ground and performing more complex maneuvers. So this is something I've been working on for a very long time. So I grew up flying radio-controlled airplanes. This is sort of peak fashion sense when I was 11 years old wearing that tie-dye shirt. And then, as Claire mentioned, I was kind of fortunate to be starting grad school at MIT around the time when it was first possible to basically take RC airplane equipment, so to take the motors and servos and power systems that had come out of the RC hobby and start putting computers and sensors on them. So this probably looks familiar to at least some of you. This is a quadcopter from about 2008. So it's carrying a LiDAR and cameras and a fairly powerful computer. So this is what our lab started working on at the time. And really, the first task here was essentially to take ground robot technology and try to make it fly. So the key technology was using laser-based scan matching to first just do basic stabilization, and then to be able to explore and build maps. So this is kind of a snapshot of what it looked like. 2008 wasn't that long ago, so the video quality probably should be better here. But maybe we couldn't afford a better video camera in our lab. So we had to speed it up to 20 times for it to look at all impressive. So it was really going at a crawl, exploring and building this map. When I got to the lab, one of the things I was interested in doing was trying to push the frontiers and sort of force ourselves to do something that was much more aggressive. So this is a plane that we designed and built. So we were basically using the same sensing and compute package. You can see the same LiDAR on the front, a couple of nice grad student touches. So the whole thing is rubber banded together, which meant that when it crashed, it was easy to fix. And after we broke two $5,000 LiDARs, we put that little cattle guard on the front to try to preserve them. So there was a ton of work to get this system up and flying. I'll skip over most of it, but the end result was really cool. So this is the video sort of near the end of the project where it was flying autonomously, for some definition of autonomous, around the parking garage below this data center. So this was a 10-minute flight. But the big caveat here is that we had pre-mapped the space and we had pre-planned the route. So there were still a huge number of algorithmic and just kind of engineering challenges in getting the system up and running. But it was not the kind of thing that you could turn into an actual product. There were a bunch of limitations there. It had all the sort of grad student duct tape holding it together, both from a hardware and a software perspective. But I think a lot of what we learned here formed the foundation for what we built now at Skydio. And this sort of demo of what was possible, I think for us was a big part of the inspiration. Like if we could take this kind of capability and make it available to anyone, anytime, it seemed like that could enable a lot of really, really interesting, cool stuff. So I'm going to switch gears now. And I think because we have a technical audience, I think it's interesting, hopefully it'll be interesting, to take a slightly deeper look at what it takes to build a fully autonomous flying system. So this is kind of a high-level sketch of a lot of what's in play in our system at Skydio. So there's a bunch of different individual components, and I think on a lot of these individual areas, we've really pushed the state of the art and developed new stuff. Like if we were a research lab, we probably would have published papers in each of these areas. But of course, the real magic is making them all work together in an integrated way on a device that works in any environment that you can take it into. So all this stuff is better seen just kind of in action. So this is how the drone sees the world. So it has 13 cameras on it looking out in every direction. There's a higher resolution user video camera. So this is what captures the final output for whatever application. So here it's again following and filming somebody. And then we have these 12 navigation cameras, which are lower resolution, but see in every direction. And they're arranged in stereo pairs around the device. So that's kind of the starting point. You can look at the same data in a different way. So now we've projected this kind of tiny planet view of the world, which I think may be a little bit easier to get intuition for how the computer is reasoning about things when you look at it like this. So the first really foundational problem is a very, very simple one. It's just knowing where you are and how you're moving all the time. But even this is a pretty significant challenge, and most systems do this using GPS. So if you're flying high enough, if you're outdoors, if you're above all the tall structures, you can just use a GPS signal combined with an IMU. If you're not, if you want it to work all the time and you want it to be super precise, you need to do something else. Some of you are probably familiar with how these kinds of algorithms work, but basically we're tracking these features in all of the images. So if you look at these trails around, those are areas of high texture that we can associate both over time in the same camera and between cameras. And then essentially each of these little feature points becomes like a navigation beacon for us. So each of them is now projected out into 3D in the center there, and we can estimate where they are with a few centimeters of accuracy, and that gives us a super accurate of the motion estimate of the vehicle. So this means at any given time we can say with super high confidence where we are, how we're moving, and this is really the foundation for everything else that we do. So I'll talk a little bit about how we build up a map of the environment once we have the state estimate. So the high-level sketch of how this works, so the cameras are arranged in stereo pairs. We do stereo matching, similar to what a person does. We have two eyes. You can look out. If you can associate the things that you see between your left and your right eye, you can triangulate how far away they are. So there's a lot of complexity in terms of how this actually works, but that's the high-level concept. We can then project that out into 3D space and then use that over time to aggregate and build a 3D map. So this is a sketch of the stereo images from each of the individual cameras, and then yeah, so these are the stereo images from each of the individual cameras, and then you'll see that get built up into the 3D volumetric map. So this is what the full 3D environment looks like. And then that snake extending out in front is the vehicle's prediction of what it's going to do based on everything that it sees and the motion of the person that it's trying to follow. So the theory here is fairly straightforward. In practice, building an autonomous system that works in all the different kinds of environments that people actually care about is incredibly challenging. So these are just a few, I don't think these are even the worst, but this is sort of the horror show of real images that you can run into for people actually using these things in the real world. So you get a bunch of repeated structure, transparent reflective surfaces can be difficult. The sun can cause huge challenges for the visual appearance of what you detect. Then you also get textureless surfaces. If you look at those images on the right, it's, are we looking at the sky? Are we looking at a wall? How far away is it? It's extremely difficult to tell from this kind of thing. So the real key to making this work turns out to be pulling in more than just the straight photometric stereo information. So we have systems that use sort of semantic context, so higher level knowledge of what you're looking at to estimate how far away it is. So this is something that we've done quite a bit of research on. We've actually published a paper on a couple of years ago. But the idea here is that we're leveraging the power of convolutional neural networks to build up a semantic understanding of the scene and then combining that with photometric information. So we do this kind of lower level processing where we extract the deep features, we convolve them to get something analogous to the cost volume that you would get in a traditional stereo pipeline. And then out of all of that, we can predict depth, which takes into account both the semantic and the photometric information. So these kinds of things tend to move fairly quickly. Like when we published the paper, We were tops or close to tops on the Kitty benchmark data set. Since then, the benchmark has raced ahead. We've also raced ahead in kind of a slightly different direction that's more relevant for what our product actually needs. But we're very bullish on this as a building block towards learning for these kinds of systems. So the really exciting thing for us is we think that this kind of technology can form a foundation for a wide range of different kinds of applications. So our first product with the software set that's available now is essentially this like professional film crew that fits in a backpack. So it can autonomously do all the kinds of things that would be possible if you had a Hollywood person there with a boom and a crane and a dolly and sort of directing the shot themselves. So these are a couple of examples of things that we call cinematic skills. So basically these are high-level behaviors that are built on top of the core autonomy engine, which you can think of in a lot of ways as analogous to a game engine. So it solves all the sort of low-level physics. It's a very complex piece of software that has to run in real time. But once you have that, you can build a huge number of things on top of it. So these are things that we built that are available on our product now. But we built all of them with the same framework that we're now exposing in our SDK. So the key idea here is that it abstracts away all the complex sort of low-level stuff that you need to do, like thinking about the 3D structure of the world, detecting different kinds of objects, predicting into the future, and allows people to think at sort of the much higher level of just what they want to accomplish. So this is in private beta now. So we're working with a couple partners who are building some interesting stuff on it. But we're pretty excited about where this can take us. So this is a very early prototype of kind of a different kind of use case. So drones are fairly popular with real estate, although again, you run into the same problem of it's dependent on the skill of the pilot. So what I'm about to show is a fully autonomous real estate thing where we basically just told it where the front door of the house was and it did the rest. So it's planned out a series of autonomous shots to capture the house in an interesting, compelling way. And the key thing here is that it's doing all of it without having to worry about running into anything. So if you'll notice, it weaves its way around a couple of thin wires here. You can basically just plop the thing down and trust it to get this kind of footage fully automatically. And then a different kind of example, collecting aerial imagery to do a 3D reconstruction. So here we're telling it there's a structure here that we want to be able to build a map of, and it's planned out all the different vantage points that it needs to do that. Again, being aware of obstacles, planning its way around things when it needs to. So you can basically just push a button and have it go off and do this kind of task. And then the end output of this are these high quality 3D reconstructions. Yeah, so we're very excited about where we are right now. I think that, as I mentioned at the beginning, this story over the last few years, I think in drones, has maybe been this gap between excitement around what's possible, or excitement around what seems like it should be possible, and what you can actually do with existing products. And I think, like a lot of new technologies, a lot of new industries, this stuff is all real. It just takes longer to develop than people originally thought. And we think that full autonomy, the ability to perform complex tasks at or beyond the level of the best human pilots in the world, is really going to be one of the key enablers for this. So we're excited about what our first customers are doing now with R1. The response has been pretty overwhelming, but we're also, of course, excited for what's to come. We think this is really the beginning of the wave of a lot of the most exciting drone stuff coming to life. So thank you again for having me, and I'm happy to answer any questions.
Great product. Do you see whether your vehicles should be talking to each other? If there's a, let's say, group of runners and they all have one of your device, or do you think that's not necessary?
So I just happen to have this perfect video queued up for this. So here we have, this is Jack on our motion planning team, and Jack currently has 4 vehicles following him. So you can get a glimpse. This is on the company retreat. So building autonomous drones is also a lot of fun. My general position on this is I think that there's all kinds of interesting, cool things you can do with multiple vehicles collaborating. Like film people go down water slides, I guess. But I think that the thing that makes that possible is you need to be able to trust them all to fly themselves in a useful way first. And so we do think that our technology can be an enabler for having fleets, massive numbers of drones, doing interesting, cool stuff, collaborating, avoiding running into each other. But the starting point is really being able to do all that stuff well with one. So this is something, having multiple drones, building out different kinds of use cases and experiences there is definitely something that with this foundation in place, we're going to be doing more of going forward.
Yeah, I'm curious about agricultural applications, and I see a lot of your presentations about navigation and detection in that navigation, but what I'm run across is software, the lack of software for detection in agriculture. I was wondering if you guys have looked at that.
So agriculture is not a particular focus of ours, because I think that agriculture is actually one of the applications that works reasonably well with the kind of current paradigm of drones that essentially act like low-flying satellites, like they fly high overhead, look down, and take aerial imagery. I think the other part of this, which is maybe more what you're asking, is I think for a lot of these commercial applications, the drone is really just the first piece of the puzzle. And in order for the product to be useful, there's a lot of other software that needs to exist to be able to process the data and extract insights. And I think this is another thing that has to come together for a lot of these applications to really take off. And I think we're starting to see that in a few areas. But I think a lot of this stuff is going to take many years and collaboration between multiple companies and getting feedback from customers to have this sort of full end-to-end thing where you can just push a button, 1 or 10 drones go off, and then you get back the information that you care about in a nice, summarized way. So I think it's coming. I think it's just going to take a little while.
Question in the back here, right here. So this is very nice work, but one of the challenges is there's a lot of airspace that's restricted. So on the Berkeley campus, I cannot fly a drone in most places. Most of San Francisco, I cannot fly. In the city parks, I cannot fly. I cannot fly it in Point Trees. I cannot do it in Big Sur. I cannot do it in any of the public beaches. Right. However, Skydio has a great advantage, right? You can make autonomy guarantees. So are you guys doing anything to start a discussion with the FAA to open up the space?
Yeah, that's a really good question. So my first thought on this, somebody had a great observation, which was that if automobiles were invented today, they would be banned immediately, which I think is totally true. Just think about the risk that we incur every day from these heavy, noisy things. And so I think generally, drones face some of this kind of new technology adoptance issue, and a lot of it I think is grounded in really legitimate concerns around safety and privacy and noise and other stuff. Our overall view on this is that basically all of the challenges have product answers. And as you say, I think autonomy has a lot to say about this, because with an autonomous drone, you can kind of shift the paradigm from this crazy thing that could do whatever it wants at any time, depending on the whim of the pilot, to something that behaves according to the rules, where basically you can take whatever the rules are and turn them into software and just guarantee that it's going to obey it. And so, we've talked to folks at the FAA. I think generally they understand this and they're excited about it, but they're also working in a world now where 98% of drones are manually flown. And so I think that over time the regulations will evolve to reflect what autonomy brings to bear. I think in the short term, our goal is just to do everything we can to encourage customers to use these things in a safe, responsible way and make our product as reliable and safe as it can be. And I think ultimately, as the products get better, more people use them, acceptance will grow. It's just, again, going to take some time.
2 questions. You showed early work on fixed wing airplanes with LiDAR sensors. So I'm wondering what other sensors you're focused on video now, it looks like, cameras. Are you looking at LiDAR still and other sensors like that? And are you also looking at fixed wing in addition to quadcopter?
So we made a really big bet on computer vision when we started Skydio for a bunch of reasons. Like I think that we'd used LiDAR as grad students. We'd also done a bunch of stuff with vision and cameras. As grad students, we didn't have to care about building a product that had a reasonable cost, and so we could buy $5,000, $10,000 LiDARs. Cameras are super cheap, they're super light, which enables you to build lighter, smaller, quieter, cheaper vehicles. And I think generally it's a much richer source of information. Like LiDAR can tell you how far away something is at a single point in space, but there's just a tremendous amount of like context and information in a single image. The challenge is extracting that information. I think when we made this bet 4.5 years ago, it looked a lot shakier than it does now. I mean, this was right at the inflection point with deep neural networks. And I think my overall view on this is that there will be some applications where other sensors matter, but I think for the vast majority of stuff, the vast majority of use cases, vision is going to solve it because the algorithms will keep getting better, the sensors are going to get better, and there's really nothing that could challenge a passive image sensor in terms of cost and complexity. Like it's just a passive piece of silicon that soaks up photons. In terms of fixed wing, the short answer is I think that there's a lot of exciting stuff that you can do if you have a wing. I mean, we saw examples of that with zipline, but you can just fly faster and further and be quieter. I mean, I think that a lot of things get better if you want to be able to do that and hover in place and fly very precisely. That induces a new set of challenges. But I think this is something that we will see more of going forward.
Yeah. So about the have you focused, like a lot of companies have focused on like large groups of drones, like 20 drones say, and just working very well like together in a huge group. Have you focused a lot on that or no?
So we've done, I showed the video here, like we've played with swarms and drone coordination some. Our overall view is that for most interesting applications, like you want to be able to solve the sort of individual autonomy problem first, and once you can do that, you can scale it. So I think we'll see more of this going forward.
Yeah. How about application indoors, especially in low or no light situations with onboard lighting?
So I don't have any videos here, but the system is fully capable of flying indoors now, as long as there is some light available. Because we're using vision, like we don't need GPS, it can fly in very confined spaces. So flying indoors isn't a problem. In lower, because we're using vision, we do depend on some available light. So I think that you could change the image sensors to be much more sensitive by an order of magnitude or two if you wanted to fly in low light conditions. If there really is zero light, you would need some form of active illumination. But there's lots of examples of how to do that, both in the visible and IR spectrum.
Hi, Adam. I think I should tell the audience that I used this thing at my wedding. It was very cool. So here's the question.
That was it. Yeah, that was the crashing one. Yeah.
I'm sure I did some things that I shouldn't have done. So he has some footage. So here's the question: do people act differently around it than they act when it's not around?
So for sure, like the first few times they use it, they do. I think that there's, it turns out to be this really cool experience. I think the first time that flies, in a lot of ways, it feels like this living thing. Like it responds to what you do. You can play with it. You can challenge it in different ways. And we see that a lot with our customers when we give people demos. I think that the really interesting thing is most people, once they sort of build up a model of like, okay, this thing's going to follow me and film me and it's not going to run into stuff, then they just like assume that that's all it's ever going to do and they forget about it in ways that are challenging and kind of scary from an engineering standpoint, but I think pretty compelling from a product use standpoint. So our experience is, what's that? Generally, no. I mean, people just assume that it's always going to work, which it does like 99% of the time. It doesn't all the time. I mean, this is like, you know, our challenge going forward is to make it just 100% totally robust. So I think that if it gets, you know, if you go through too narrow of a gap or something and it can't keep up, eventually it'll get stuck and you'll have to go back and get it, or now it'll actually use GPS to try to find its way around. So it is getting better. So if it makes a mistake, people at some level will have to respond and deal with it. But if everything's working, people just seem to ignore it. We prefer to call it subject tracking rather than target acquisition. So basically, like we've trained it to look for different classes of objects, and so if it sees an object of a class that it's been trained to look for, it will start to track it, and it'll build a unique visual identifier for it based on appearance, so based on size, color, shape, these kinds of things. And then it'll track it over time, and then there's, you know, so that's sort of the low-level piece. For different use cases, you can imagine doing a lot of different things. So for our software now, you have control over it from a mobile phone, so you can tap on any object that it sees, and it will then start following and filming that. But you know, we built demos where you can have a security thing where it just flies around looking for these different classes of objects, and when it sees one, it either just catalogs it and knows that something is there, or it can start tracking it. Right now they are. For most of the skills. I mean, we also have ones, we haven't shipped this, but we have one we call party mode, where it just flies around looking for people, and then it'll film them for 10 or 15 seconds, and then move on to the next person. Or, you know, another one that we've prototyped is like for a race, it'll follow the fastest person. So it really is like, its behavior is at the control of the software and can change depending on what you're trying to do with it.
So following up on following up on what you were mentioning earlier, can you say some more about that 1% of edge cases where you guys are finding safety challenges, and what are the main challenges that you foresee going forward?
So I mean, we try really hard to avoid anything that would be a safety challenge. Like the predominant things, and we try to make it so that the system degrades and fails gracefully. So, you know, the predominant challenge now is like if somebody moves super aggressively behind something and goes out of view, it can lose track. And so, you know, I think we sort of come at it from both ends. When that happens, you want to make the behavior as continuous as possible. So this has motivated things to like do global sort of refining using GPS, but also just getting smarter, being able to predict further into the future of what people are going to do, being able to plan further. So we have a neural network that predicts the motion of people over time based on their previous motion, which is getting better and better. So I think you know, all these things have product answers to improve them, and in a lot of ways, you know, that's the fun of doing this. All these challenges are interesting, and the more we use the product, the more we get the data to understand them and improve them.
From a robustness standpoint, which segment of your market is more demanding, the consumers or the commercial applications? And you know, how do you, in the longer term, how do you bring this to market? Can you simply sell the software modules, or is it software plus hardware, or do you have to build a full vehicle for this to go to market?
Yeah, those are both really good questions. So I think that at least for the way that people think about most commercial applications now, I would say the consumer use case is more demanding. I think that like being able to go fast through very dense environments, which people want to do all the time, is super, super challenging. And part of why we picked this as the first thing to focus on is we knew that solving those challenges would unlock a lot of cool consumer use cases and create a lot of value there, and that the stuff that we do there would transfer over into really robust navigation behavior for all sorts of other stuff as well. So I think that that kind of behavior is going to be more important for commercial use cases as well. It just isn't right now, because the ones that people are most focused on are the simpler ones where you're flying relatively slowly and collecting image data. But you imagine if you wanted to like have one of these go in ahead of a SWAT team and clear out a building as quickly as possible, you know, speed and agility would matter quite a bit there. In terms of how the sort of go-to-market evolves over time, our general view is that there's going to be a huge number of applications that are served by either the same device or very similar devices. And I think we see evidence of that now in the sort of manually flown realm. So there are a lot of people that have tried to build these very expensive, sophisticated commercial rigs, but most of what is being used in the enterprise drone world right now are consumer products. And right now the versatility comes from the pilot. In the future, we think it'll come from the software. So, you know, I think that the core capability of just being able to move an image sensor around in 3D and capture data is super general and applies in consumer. It applies for a lot of commercial applications. Not all. There are some where you have a particular sensor, some specialized payload, but I think there's a lot that's covered by that. You know, the long-term view, we think that this kind of technology does belong on everything that flies, and you know, we're not going to build all of that stuff ourselves. I think there are different ways that you can accomplish that, but I think that's a little bit further down the line for us. All right, thank you.